Now for something completely different, which is the ocean. What we're doing with AWS is we're trying to figure out whether climate change is going to break the ocean. Or to be technically a little bit more precise about it, whether the multiple synergetic and compounding stressors of climate change are going to push the ocean to a potentially catastrophic tipping point, not in the next century, but within 1 or 2 or 3 decades. That turns out to be a wicked problem. It's a very difficult problem, which we cannot solve without the massive capacity of AWS. So let me take a step back, literally, and let's take this problem from the beginning. You and I go to the beach for solace. We sit in the dunes and we look out and we look at the ocean, and it seems a soothing, wonderful, simple thing, a big slab of gray or blue. But of course, intellectually, we know that our senses are very much deceiving us. If we could roll the... what really is happening is what you see here to your right and left. It's a glorious mess. It's an incredibly complex system. It's a complex physical system in this beautiful animation here, which looks a little bit like a Van Gogh painting. It shows you the Gulf Stream, how it's generated in the Gulf, and it sweeps around Florida. By the time it hits Carolina, it's moving at about 9 million cubic meters per second. By the time it gets into the mid-Atlantic, it's about 20 million cubic meters per second. There's endless subvortices, subcurrents going on. It is one of the most complex physical systems that you can imagine, hydrodynamic systems imaginable. And it's only one of so many. And it distributes energy around the world. It makes Europe as we know it possible. It has huge implications on climate and so on. Now, as we dip below the surface, we will notice that it's not only, of course, the surface vectors that are going on, the surface forces, but there's incredible vertical forces going on. There are massive amounts of heat exchanged up and down from the equator to the Arctic and back, stirring up the layers, bringing up nutrients, distributing energy, making weather. I mean, just the physical system of the ocean is a stunningly complex beast. It feeds a biological layer on the other side, which is equally as complex. This is a beautiful animation of a kelp forest in California. Everything, as you know, is connected in the food system. The ocean makes about 100 million tons of microbes per hour. And those 100 million tons feed about 800 million tons in total of fish, of predators. So the amount of energy transfer that's going on is insane in the ocean. And it's all fed, of course, by physical forces, by the transfer of nutrients, by the bringing up of nutrients. And so the physical side and the biological side, are working together. And so now we're taking this complex system, which we all need. We need it because it makes half of the oxygen that we breathe. We need it because it absorbs 93% of the energy, the excess energy of climate change. We need it because it makes food. We need it because it distributes energy and makes our weather bearable on this planet. We take that complex system and we stress it. We run the largest science experiment ever devised, except it's a completely uncontrolled science experiment. We're stressing it, we're adding heat, we're adding acidity, we're overfishing it, we're adding plastics, we're adding pollutants. And so the question is, what will it do? Now, it's very interesting what complex systems do when you stress them. Because the more complex and the more interconnected the system is, if you put an even stressor on it, even if it's a gradual stressor, at first it's actually pretty resilient, right? Because when one thing goes up, some other thing goes down. It's very interconnected and it evens itself out. At a certain point, though, the whole thing tilts. Typically, the system at some point goes over a tipping point, and then it crashes hard. It crashes catastrophically, and it crashes very quickly. And if we go back in time to geologic eras when there was a similar change going on, like 50 million years ago, for example, there was a time when the CO2 content in the atmosphere went up to about 800 parts per million, just like now. when the temperature went up to 6 or 7 degrees, just like it's now going to do. And the ocean changed in very fundamental ways. We had mass extinction events, and major currents went north when they used to go south. If that happened again today, it would be catastrophic for us, for our civilization. And when it happened fast, within decades. So it's pretty reasonable to ask, is that gonna happen again? We need to know. As ocean conservation people, we need to know. We need to know as climate people, because the feedback mechanism between the ocean and the climate system is, of course, intense. You could imagine what happens to the climate system if the Gulf current doesn't flow anymore, or if the primary biological productivity of the ocean crashes and you don't have uptake of carbon anymore. The feedback back to the climate system is insane. But now we have an analytical problem of daunting proportions, because of course you can't take all the data that we have about the ocean, oceanography data, put it in a big data hopper, turn an AI crank, and out comes a prediction of what the ocean is going to do in 20 years. That would be like predicting the weather on April 27th, 2026. We cannot do it. There are limits to what can be done. So with AWS, what we're doing is we're applying some of the tools from other disciplines which are analogous in the sense that they have to somehow take an incredibly complex system like an economy or like the internet and keep it within the bounds of some level of control. We're taking their tools and applying it to this problem. And the way that we're doing it is we're looking at the ocean as a system of discrete states. So a state may be the population of sharks, or the population of plankton, or maybe the temperature. Each one of those states, which collectively make up the ocean system, each one of those states wants to be in an equilibrium, but can't quite be in equilibrium because every state is connected to so many other states which are tugging on its equilibrium. So you have this basically a network model of deeply connected states. Now, we then apply pressure to that model, we make it hotter, we make it more acidic, all the things that climate change does, and we see what happens. And in fact, we apply the world's largest Monte Carlo simulation. You can imagine that with 70 or 80 states, infinitely connected, over a time period of 50 years, with full sampling, and every one of the samples is a Monte Carlo model of every connection with everything else, the data intensity of this is completely crazy. And AWS does it beautifully. And we are now able to do things that we were not able to do even 5 or 4 years ago. And the important thing is that the climate modelers really need this information, because the big climate models that we all rely on are not very good at predicting failure. They're good at predicting equilibria. They're process models that do equilibrium projections. We're doing basically a state model that predicts whether or not you're going to have catastrophic failure. And it's in the interplay between the two that really the good stuff is. So the climate modelers are really interested in what we're doing on the failure models, and of course vice versa, and we're working together. So this is going to be incredibly important to us as ocean people, and to us as citizens, and to us as people who are deeply worried about climate change as well. In closing, what I'd like to say is I get often asked as an environmentalist, do you still have hope, and so on. One of the things that really gives me hope is I have a strong sense that the rate at which we're starting to understand the complex Earth systems and their dynamic behavior is faster than the rate at which we're screwing them up. That our understanding is now getting to the point where we're really understanding the dynamics behind it, and that we might be getting ahead a little bit in our fight to really understand what it's like to live with 8, 9, or 10 billion people on this planet and taxing it the way we do. And the capacity of an AWS to come in here with the full force of their cloud is just absolutely essential in it. So thank you very much for your time.